Hey guys, Penwell here, and today I want to talk about a number that I think nobody ever gives enough respect to, especially ones that are uneducated or the people who watch my videos who aren't big in math. But I bet you've heard of numbers such as 1, 67, pi, 0, -1, but have you ever heard of this number? I, the imaginary unit. You may be confused, like, what is I? Like, how do we make a new number? Well, I'll explain it to you, and it's all gonna make sense. So I'm gonna tell you all the properties of I, hence why this is called the Imaginary Numbers Deep Dive. So, let's get into it. Oh, and if you guys are wondering, yes, I did switch to the whiteboard because it's easier to use, it's more satisfying, it's bigger, and the trees are dying, so we gotta save the trees. No more wasting paper, no more trash. Okay. Sorry, I had to move my this person's hair. So let's start with the basics of imaginary units. First of all, I know a lot of you probably aren't aware of imaginary numbers, but I bet some of you are aware of these things called quadratics, which are basically a second degree polynomial with like x as a hidden number. And since there is no middle x term, we don't need to use the quadratic formula. I'll explain that in another video. Let's just subtract 1 from both sides. X squared equals -1. That seems pretty simple, but what is x? First of all, let's recall that 1 times 1 is 1, -1 times -1 is also 1. Positive times positive is positive, negative times negative is also positive. And x equals square root of -1. But wait a minute, how do we get the square root of negative numbers? Well, in the real world, it's undefined. If we want like the world to exclusively have real numbers, then yeah, this is where it ends. No more I. No imaginary numbers. The end. Okay, I'm just kidding. But in the imaginary world, a lot of mathematicians just defined the square root of -1 as a new number called I. Specifically for this equation, the solutions would actually be positive and negative I. But we just say I because that's a lot more simpler and it gives you the full definition. There are two big things with I. First of all, complex. Like, imaginary numbers are not the biggest system of numbers, because what if we had a real number and an imaginary number put together? Well, you have the complex numbers. These are really useful when we're trying to use like square roots or other imaginary stuff, so it's very useful. Some of these complex numbers can include pi plus 2i, 1 plus I, or 4 minus the square root of -5. And here's another one. So here's the number line. I drew a point at 1, and when we multiply by -1, you may be thinking in terms that we just flip it to the other side. But what if I told you this could be better notated as a 180-degree rotation, I mean. And you might be wondering why. Like, what if we integrated I in the number line? Not just that, not just including I, but we can make a 2D complex plane, so we could also put in 1 plus I, -1 plus I, -1 minus I, and 1 minus I. This lets us graph any complex number. Like, literally, every number you can think of that's in the realm of complex, imaginary, and real numbers, it's on here. And guess what? Using I as the square root of -1, this gives no contradictions. This is entirely possible to use. This isn't undefined. Well, it is in the real world. But defining imaginary numbers, it just adds to our number system, which I think is brilliant. This is your face right now. Ah! Yeah, imaginary numbers are wonderful. Okay, so first off, let's explain some other things we can do with imaginary numbers. Like, here's one thing I like to show. I actually appears in this like recursive thing. x equals 1 minus 1 over 1 minus 1 over 1 minus 1 over 1 minus all in all forever. And you may see that this thing is actually the same as this thing, so we can just substitute x into that. X equals 1 minus 1 over x. But wait a minute, look, as you go by iterations, you just get 1, 0, undefined, 1, 0, undefined. Yeah, it doesn't look like imaginary numbers would be there, but trust me, if you multiply both sides by x and then move everything over to the left side, you get a quadratic, so we can use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, and when we do that, we get negative 1 plus or minus I times square root of 3 over 2. This is not only imaginary, it's complex, yet also algebraic. I'll tell you about algebraic numbers later, but guess what? You might think, is this like the average of 1, 0, undefined? The thing is, no. In fact, if you just kept doing this series forever, you would never reach this. This series doesn't converge. Yet, it does. Our math checked out. But one thing I did prove is that I is in quadratics. It's in a lot more quadratics than you think. In fact, a lot of mathematicians, before imaginary numbers were defined, they usually just thought these sort of quadratics were pointless. They ran into these quadratics a lot. But one thing you'll know is that I can be everywhere. Okay, anyways, let's ask more questions about complex numbers. Alright, so we know the basic operations, plus, minus, times, and divide. But what if we use those basic operations for two complex numbers? Well, addition's pretty straightforward. You just add the real part and add the imaginary part. For 5 plus 2a plus 3 plus 4a, if you do the math, you should get 8 plus 6i. For subtraction, it's pretty much the same, except you subtract the real value and you subtract the imaginary number. So 5 plus 2i plus 3 plus 4i, that turns into 2 minus 2i. Alright, multiplication, this one is a little fun. We use FOIL. You multiply the first terms, outer, inner, and last. This works for any a plus b times a plus b equation. And this would turn out to be ac plus adi plus bci minus bd. So, using these same two example numbers, 5 plus 2i times 3 plus 4i gives this equation, and simplifying it, 7 plus 26i. A little bit of a random number. Oh, division's where it gets juicy. You have to multiply the numerator and the denominator by the conjugate of a denominator. And you might be thinking, what is a conjugate? Well, a conjugate, we usually use the symbol z to represent a plus bi, and a conjugate is just flipping the sign. For example, 2 plus 3i, the conjugate is 2 minus 3i. This one is pretty easy. Because you multiplied this, you get this fat equation, and then you can separate the terms, and ac plus bd in parentheses over c squared plus d squared plus bc minus ad all in parentheses over c squared plus d squared, add the I to the end. I did this for 5 plus 2i and 3 plus 4i, and I got this fractional result. And if you're not into fractions, I also did it in decimal. And guess what? This is a perfect approximation because 25 is a really cool number because its reciprocal terminates. So therefore its decimal terminates. And yeah, and you might be asking, well, can I do all of this even if one of the numbers is just plain pure real or another is pure imaginary? Well, yes, you can. You just have to sub in the other parts for 0. Like a real number can be written as a complex number, a plus 0i, and and a purely imaginary number, 0 plus bi. So those were the basic operations. Now, here's one of the coolest equations in math. Or, I don't know. One of my favorite imaginary number solutions is if the square root of -1 is I, what's its square root? Well, first we know the square root of I should be written as a plus bi, a complex number. You may be wondering, would the square root of I just be another kind of sort of imaginary number? And the answer is no, it's actually a complex number. We just square both sides, I equals a squared plus 2abi minus b squared. We can do something called pairing coefficients, where 0 equals a squared minus b squared, 1i equals 2abi. So we can set these, so 0 equals a squared minus b squared. That means a squared and minus b squared are additive inverses since they both equal 0. So therefore a squared equals b squared. This is very useful. I equals 2abi. So therefore we can do 1 equals 2ab over 2. This is kind of another way I did it. I kind of had to use my own brain, so there might be simpler solutions to this, but here's how I did it. Half equals ab, divide both sides by a, so 1 over 2a is b. Now we can turn that into b squared, and we have 1 over 4a squared. So we can, and since a squared equals b squared, we can substitute that in. B squared equals 1 over 4 times 1 over b squared. So therefore, multiplying both sides by b squared, b to the 4 is 1/4, b squared is 1/2. B equals plus or minus 1 over root 2. And guess what? Since a squared and b squared are equal, we can just flip these, and a also is plus or minus 1 over root 2. So we just plug those in. So our final answer is the square root of the square root of I is plus or minus 1 over root 2 plus 1 over root 2i. Wow. And if you do the multiplication for this, it checks out. Oh, and just so you guys know, the negative of this would be negative 1 over root 2 minus 1 over root 2i. It would change it into like it's, I don't know. Anyways, now, these are some normal basics of I. Some regular ones, but what if I told you that I helps a number's transcendence? It helps us prove that a number is transcendence, and I'll show you. I'll use already made theories, and I won't explain them because they're irrelevant and they're hard to explain. One of these is the Gelfand-Schneider theorem, and this theorem is so long to explain. It doesn't even deserve its own video. I just don't want to do it, but you can trust me, okay? Look it up. Alright, anyways, here's a new question. Alright, before we prove a number's transcendence, we have to talk about this equation. E to the power of I pi plus 1 is 0. This is the most famous equation in math because it links 5 fundamental constants. First, let's talk about 0. It's the additive identity. 1. A times 1 over a, it's the multiplicative identity. 1 is the number we start counting in. But what the hell are e and pi? First, let's define e, because this one's pretty interesting. E is approximately 2.71828. So let's start off. E is related to derivatives, which we talked about last time. But we have not talked about the derivatives of exponential equations, because this comes out to be the natural log of the base multiplied by the base raised to x. So let's talk about it. The derivative of 2 to the x, it's roughly around 0.69 times 2 to the x. The derivative of 3 to the power of x, around 1.1 times 3 to the x. The derivative of 2.5 to the power of x, 0.91 times 2.5 to the power of x. Now you ask yourself, which one of these bases can be 1 times itself? And since 1 times the function is just the function, can a function be its own derivative? And the answer is yes. E to the x. We define e as its own derivative. 1 times e to the x is still e to the x. We approximate its value, it's 2.71828. But since the natural log in e create 1, the multiplicative identity, that means that e is the base of the natural log. Natural log of e is 1. That means you can also create equations like e to the power of ln x, and that equals x. I didn't write that down, but yeah. Okay, now let's explain I. Wait a minute, we just explained it, idiot. Freaking stupid. Okay. What is pi? This one more people should know. Imagine a circle. It has a circumference and a diameter. What is the ratio between it? Because it has to be a number. Like if we took the circumference and then just made a line out of it, and it turns out for a perfect circle, circumference over diameter is 3.4159, also known as pi. Now, this might seem crazy to you. How can I, the imaginary unit, link together two unrelated numbers from two unrelated concepts, geometry and calculus? How did these two come together? Well, I'll explain it to you. Okay. Alright, the best way to solve e to the power of I pi is using Taylor series. Right here. Like, let's assume that e to the x is an infinite polynomial. But you probably are asking, wait a minute, isn't a polynomial only for algebraic numbers and e is transcendental? And the answer is, transcendental numbers can be represented as infinite polynomials because infinity is not a number, it's not a degree. So, yeah, it still remains transcendental. So we can use a derivative chain to find out what all these numbers should be. And just so you know, this e is not related to this e. It's actually a constant. So let's recall that e to the 0 is 1. Now we can plug in 0 for x for all these terms, and we get e to the 0 equals a. So therefore, 1 is a. So we can just put that in right there. Now we do the derivative and power this to 0, we get b. And b, that means b is equal to 1, but since it's followed by an x term, we have to do 1 times x, which is x. Now, e to the x, we do the derivative again. Remember, I should have told you this earlier, but remember that when we take derivatives, we take the exponent down and subtract 1 from the power. So, for c, we know that 1 equals 2c, so therefore a half equals c. And we have x squared right here, let's drop it down there, and yeah, this continues. Because 1 over 6 is d, 1 over 24 is e, and I did this until I ran out of space. And you may be wondering, wait a minute, 2, 6, 24, are these the factorials? And the answer is yes. E to the x, the polynomial for it is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, on and on forever. So now we know what e to the x should be. And guess what? We can do the Taylor series for other functions, and here are 2 more. Okay, so you know about trigonometric functions like sine, cos, and tan? Well, guess what? They have looping derivatives, like the derivative of cosine of x is negative sine of x, derivative of that, negative cosine of x, derivative of that, sine of x, derivative of that, cosine of x. Because of this looping effect, it's really easy to use it for the Taylor series. And what we found out about this one may surprise you. So, of course, I'm just going to scroll through all these steps because I already explained what happens. But at the end, we get cosine of x equals 1. Oh, wait, I should explain that all of these that say 0, yeah, we just ignore those. So we actually have an alternating factorials with plus or minus. Cosine of x is 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 720, all the way forever. And you might see that this one is pretty similar, but the next one we do will definitely like put everything all together. Let me show you. Oh, just so you know, we are using radians, not degrees, because when we use radians, I mean, if we use degrees, we would have to have like a coefficient pi over 180 or something. So to ignore it, we use radians. And radians is very useful because it involves pi. It's used in circles. Alright, it took me a long time, but I did the Taylor series for sine of x. This will help us bring... This will help... This is... This is the other half. Oh my god. This is the other half that will help us combine it with cosine of x to help us get something related to e to the x. So I did all the same steps. I really don't need to write them, but I do it because it's fun. But we come out with x minus x cubed over 6 plus x to the 5 over 120. Hold on a minute. I forgot to write something. Let me just write it real quick. There we go. You might be wondering, this is 3 factorial, 5 factorial. It's the odd number factorials we're adding up now. So since we had the even ones with the cosine, and now we have the odd ones with the sine, you know what that means, baby. All right, now we have all 3 of these Taylor series together. They look similar. Can we combine them? Yes, with one special number we can add alongside x. That special number is, say it with me, I. So e to the ix, if we plug in I, we get 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the power 4 over 4 factorial, on and on forever. The ones that are underlined are the cosine of x terms. Yeah, see here, they're the same. But the sine x terms, they're also the same, but they're multiplied by I. So we have I times sine of x. So e to the power of I times x is actually cosine of x plus I times the sine of x. This is Euler's formula. And that's why an exponential function raised to the power of I times x equals 2 trigonometric constants in terms of radians. And of course, if we plug in pi, we have cosine of pi plus I times the sine of pi. That becomes e to the power of I pi equals minus 1. Moving minus 1 to the left side, e to the power of I pi plus 1 equals 0. And guess what? If we divide pi by 2, we get I, and negative 1, negative I, and 1. And those are the power, that's the power chain because, and that's the power chain of I, because we'll actually return back to I at e to the power of I times 5 pi over 2. That means e to the power of I times x can be represented as e to the power of I times x plus 2 pi k, where k means any integer. So that means the natural log of I is multi-valued. Yeah, it doesn't have one single value. The principal value, though, is the most simple one, which we use this. So the natural log of I is I times pi over 2. Yeah. Okay, so we already proved that the natural log of I is just I times pi over 2, but there's also another way of solving it. So we have we have the complex plane. Ignore all these arrows, they will be better explained later. Anyways, we can plot A, which is on the real axis, and B as in the imaginary axis. And now we have our cos theta and, hold on. Our cos theta is this one, and our sine theta as that one. We can now use those as A plus BI, so we can plug it in as r cos theta plus r times I times the sine of theta. We can factor out r, so it's r cos theta plus I sine theta, and guess what? That's Euler's formula, so that turns out to be r times e to the I theta, with r being the distance from the origin, and theta being the angle counterclockwise from the positive real axis. So now we can use this to find out what the natural log of I is. Because of the properties of logarithms, we can split this into addition. So ln r plus ln ei theta. Of course, r is 1. Of course, r is 1 because the distance from the origin is 1. So a natural log of 1 is 0. So we just ignore this, and we're left with natural log e to the I theta. And natural log of e cancel out, so we're left with I theta. So the natural log of I is I times pi over 2. Bet you saw that coming. So we have I plus I equals 2i, and I times I is -1. I to the power of I is, we can solve this now since we know the natural log. We can scramble this around, e to the power of I times natural log of I, e to the power of I times pi over 2, e to the power of -pi over 2, which is a real number. 0.20788. That's a real number. Of course, this is the principal value because, look, even though we have a 90 degrees, we can actually rotate around and end up in the same place. So we can add another 2 pi, just like we said. Okay, where did I write that down? Yeah, so e to the power of I times pi over 2 plus 2 pi k. K being just an integer. Now, this can also help us find the natural log of negative numbers, because it's actually the natural log of the real number. The natural log of the real number, I mean the absolute value. So for the natural log of -2 would be the natural log of 2 plus I pi, because 180 degrees sends us to the negative axis. So yeah, or of course we could add another 360 degrees and end up in the same place. So yeah, it can also be 2 pi k. We add 2 pi k. And to solve a complex number, and the natural log of a complex number, we first have to find its distance from the origin. And the distance from the origin for the complex plane is the square root of a squared plus b squared, which is similar to the Pythagorean theorem, because on the bottom, the horizontal, that's the real, up imaginary. So we have a diagonal line, which is our hypotenuse. So this ends up being the square root of 29. We sub that in for square root of 29. We have EI. And then we have to take the argument of z, which would be the tangent of -1 of y over x in radians. So that would be tan -1, 2 over 5, 0.381. So this is 5 plus 2i in polar form. Alright, now we can prove a number's transcendence using I. And P.S. This part was actually recorded before I explained why E, pi, and I are all connected. Because if I put this part beforehand, it would be very confusing. It would make the video awkwardly stitched. But let's just get into it. There are 2 theorems in this that I'm not gonna show you the whole proof, because that would make the video so long, hard to explain, and it would waste a lot of marker. And it's not relevant. But these 2 theorems are the Lindemann-Weierstrass theorem. If A is a non-zero algebraic, then e to the power of A is transcendental. Yep, and the Gelfand-Schneider theorem. And if A is algebraic and B is irrational and algebraic, then a to the power of B is transcendental, but A is not 0 or 1. You may be wondering, what is an algebraic and a transcendental number? An algebraic number is a number that is a solution to a polynomial with integer coefficients. Like this polynomial, the solution to this is algebraic. This includes 4, -3, 2/3, phi, and the square root of 7. Phi being the golden ratio. Transcendental is a number that is not a solution to a polynomial with integer coefficients. This includes pi, e to the pi, 2 to the power of root 2, and the square root of 7 to the power of I. One thing's for sure is that we do treat I as an irrational number here, because look right here, can we express I as the fraction of 2 integers? The answer is no, but we do know it is algebraic. So first we're going to prove why pi is transcendental. So pi is algebraic, which means I pi is algebraic. Oh yeah, well, we have to assume that pi is algebraic first. So e to the power of I pi we know is -1. E to the power of A is transcendental. Hold on. Alright, sorry, someone came upstairs, so let's continue. So, EVA must be transcendental as this abides with the Linnemann-Weierstrass theorem. So, but guess what? Is -1 transcendental? Look at that number. Is it transcendental? You must be saying no. There's no way you're saying yes, -1 is transcendental. Otherwise, you're delusional. So because of this, I pi is transcendental. I forgot to write that. So therefore, pi is transcendental. Because an algebraic multiplied by a transcendental number is always transcendental. Okay, but why is e to the power of pi transcendental? Well, look at this. E to the power of pi, we can split it as e to the power of I pi times to the power of -1. Hold on. Sorry about that. Why e to the power of pi is transcendental? Well, we can say e to the power of pi, that's just e to the power of I times pi to the power of -I, because I times -I is just 1. So we know e to the power of I pi is algebraic, and -I is algebraic plus irrational. Because of the Gelfand-Schneider theorem, that means e to the pi must be transcendental. But guess what? We don't know if pi to the power of e plus pi, e times pi, or e to the power of e, like all of those numbers, we don't know if they're transcendental or not, and they're not relevant to this video. So now we know that it's in both of these proofs. I helps us know a number's transcendent, so it's pretty damn useful. Okay. Alright, now to end us all off, we're going to talk about some misconceptions. Like some people trying to attempt that the imaginary like I sometimes results in contradiction. So first, here's one. E to the power of 2I pi equals 1, but e to the power of 0 equals 1? Shouldn't that mean these are both equal? And that means, so like each of these would have to equal 0? Or at least one of these? Well, the answer is no. Because the logarithm and complex logarithm aren't the same. Because these are not the same number, they're just multiple solutions. Because in the natural log of 1, if we're talking about real numbers exclusively, it's just 0, but it can also be 2i pi, 4i pi for the complex numbers. It's any 2 pi ki, where k is any integer. And another one is trying to prove something. 1 equals 1. 1 equals square root of 1. 1 equals the square root of -1 times -1. Because of this rule, square root of x times square root of y is square root of xy. So 1 equals square root of -1 times square root of -1. 1 equals I times I. 1 equals -1. That's not true. What's the mistake? Well, the mistake comes from here. This doesn't apply for imaginary numbers. Yeah. We decided that. Because making this rule also doesn't lead to any contradictions that it should work for imaginary numbers. And here's one thought. What is I tetrated to I? Because we have succession, addition, multiplication, and exponentiation all defined. Well, the problem is we don't know how. Because since tetration is so rare, we're never really going to need it. Because you're just powering I by itself I times. There's no way you can define that. And there's no system like any drop-down superlogs that like connect to anything. So sadly, I tetrated to I is undefined for now. This means that other hyperoperations like I pentated to I hextated to I heptated to I. Someone's at the door. I gotta pick that up. Okay. Thank you for listening to my explanation of the deep dive for I. Love you. Mwah.